All right, good morning. We are back on to predicting our given behavior using f prime and f double prime, day 2. Now, we learned about a point of inflection yesterday, and basically, if your second derivative is greater than 0, meaning it's positive, your original function's concave up. If the second derivative is negative, then the original function is going to be concave down, and that's 2 derivatives deep. So what we're going to start with today is we're going to start with a couple clouds of knowledge. These are nowhere on your note sheet. These are really good to have. These are the connections that you need to connect a function to its derivative, and the derivative of a function to its second derivative, blah, 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 blah. Boom. First one. We know if y prime is greater than 0, we know the original function y increases, meaning the graph goes up to the left. Okay? We also know that if y prime is less than 0, we know y decreases, meaning goes from left to right, it goes down. Okay? So the next thing we're going to look at is what happens if y double prime is greater than 0. That means the function just before it, y prime, must be increasing, and we also know that if y double prime is greater than 0, we know it's concave up. Okay? Those are just some connections that we need. Okay? When we're working back from the basics, this is what we think about, right? And I didn't amortize. I didn't. Hold on. Got to hit pause. Okay. All right, I'm back. I forgot to animate my wonderful object here. So y prime is greater than 0. That means the function before it, y prime, the graph must be increasing. And we know if y double prime is greater than 0, we know the function y is concave up. Same thing. If we know y double prime is less than 0, okay, then the function just before it, which would be y prime must be decreasing, okay? And if y double prime is less than 0, we know the original function is concave down. These are connections, good connections, between y prime, and y double prime, okay? And we also know a little extra tidbit here, okay? We know that if y has a point of inflection, we know y double prime changes from positive to negative or negative to positive. Graphically, meaning it changes from concave, positive to negative. That means concave up to concave down, or concave down to concave up. And if that happens, we know that point of inflection on y is going to be a max or min on y prime. All right? Those are just little tidbits that we need to know. And they are, as they say, they are clouds of knowledge. I would make sure I write them down. These are good connectors. Because when they ask you to justify a reason, these are all beautiful justifications for us because they are calculus driven. All right? Next one we're going to look at. I'm going to give you a second here to copy this graph down on your sheet. All right? And as you're copying it down, I'm just going to blab a little bit here. On your AP test, typically in a free response, they are going to give you a graph. And they're going to say, hey, this is the graph of f, usually not f. It's going to be f prime or f double prime. And then they're going to ask you questions about f prime and f. They're going to ask you questions about the graph that you are not looking at. And those clouds of knowledge are your connections between here. So the graph of the derivative of a function f, that's why this is labeled as a graph of f prime on the interval from -4 to 4, is shown below. Answer the following questions about f, justifying each answer with information about the graph of f prime. All right? So that's what we're going to do. On what intervals is f increasing? Well, we know if f is increasing, okay, if f is increasing, what do we know the derivative is? If f is increasing, I know f prime has to be greater than 0, don't I? Hey, there's my justification. And all I need to do is look on my graph, hey, when is f prime greater than 0? Well, I can do that super duper easy. I can say it's increasing from -4 to -2, union with, that's a bad union, but then also -2 to what? +1, isn't it? Okay, because f prime is positive, the value of f prime is positive, that meant f is increasing. Well, f is decreasing when f prime is less than 0, and because this is a graph of f prime, I can see anything below the x-axis is less than 0. Therefore, I am decreasing from 1 to 4, okay? And these right here, these are my justifications. They come square out of my clouds of knowledge, all right? They're the justifies form. Then, on what intervals is f concave up or down? Remember, we are looking at f prime, right? So, when we're looking at f prime, what the heck does that mean? Well, concave up, if I'm concave up, that means f double prime is greater than 0, right? And if f double prime is greater than 0, that implies f prime is increasing, doesn't it? So these are kind of my justifications, right? Here is my justification really for it, but the cloud of knowledge is connecting when the second derivative is greater than 0, the first derivative must be increasing. So I can read, this is my f prime. Where is this graph increasing? This thing is basically increasing from -2 to 0, union with, where else is it? From maybe 3 to 4, isn't it? That's where my graph is increasing. I'm concave down. Well, that means when f double prime is less than 0. If f double prime is less than 0, we know the function from which it was derived from is decreasing. Okay, justify that. Justify it. And I'm just working through the clouds of knowledge. So then I just got to say, okay, well, f, my original function, okay, is going to be concave down when the second derivative is less than 0, or that's when f prime is decreasing. Again, this is f prime, so where is f prime decreasing? It's decreasing beginning at -4 to -2, and it also decreases from 0 to 3, doesn't it? So those are the intervals on which f, that's on which f would be concave up or down, okay? And notice my derivatives in my clouds of knowledge are connecting all three of these, all right? Then, from there, at which x coordinates does f have a local maximum or minimum? Well, because I'm looking at f prime. Well, when I'm doing this, I have to have f prime must change from maximum, from positive to negative, okay? Remember that? That means my original function f went up and came down, creating a maximum. So where did that happen? Where did I change sign from positive to negative? Local max. Positive, 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 negative, negative. I had a change right there at x equals 1. I had a change from positive to negative, okay? So maximum at x equals 1. What's my justifying? F prime changed from positive to negative. Where do I have a local minimum? Well, that means f prime must change from negative to positive. Does that happen anywhere? Because if I change from negative to positive, that means my function f goes from decreasing to increasing, making that low point there. Did I ever change from negative to positive? And the answer to that question is no, because right here I'm 0, right here I'm 0, all right? So I don't need to worry about that. So there's none exist. But remember, the thing most people forget about is they forget to check endpoints, okay? They forget endpoints for maxes and mins, okay? Well, let's look at this. Something is happening on this x at this endpoint, okay? Now notice, at x equals -4, the derivative is positive, okay? And if the derivative is positive, that's giving me a left endpoint. I don't care where you put it. And if the derivative is positive, that meant the function's increasing. That makes that a minimum, doesn't it? That makes this x equals -4 a minimum. And my justification is because left, not fat, to the right, not left. It's a left endpoint. So f prime is greater than 0 to the right of x equals -4, meaning I'm a max or a minimum value. Check it out. Check this endpoint. What's happening at x equals 4? Well, graph it out. So I've got an endpoint on the right side. I can see my derivative is negative to it. That means my function is decreasing to that point. Hey, that means that's a minimum too. So that I'm going to have a minimum also at x equals 4. I have none from changing from increasing to decreasing, but my endpoints are minimum. And that's because f prime is less than 0 to the left of x equals 4. That's my justification why that's a maximum. Or excuse me, a minimum. What are the x coordinates of all points of inflection on f? Well, remember, points of inflection on f, what are they? Well, they are maxes and mins on f prime. That's out of my cloud of knowledge. So right here I have a minimum, right here I have a maximum, right here I have a minimum. So the x coordinates at which f has a point of inflection, they're going to be at x equals -2, they're going to be at x equals 0, and at x equals 3. My justification, because f prime has a max or a min at these points. Okay? Make a sketch of a possible sketch of f. Well, here's where people are really going to squirrel their minds. Well, let me come back to my increasing and decreasing, all right? Let me come back here a second. If I laid my number line on here, okay, here's my endpoint of 4, and here's my endpoint of -4, and what am I looking at? Well, here is a 0 at -2. Well, that means f is flat at -2, doesn't it? And at +1, I have to be flat because that's an x-intercept. And then here, this is a 0 at 4, so I end up at a flat. Now, when I look at this, my derivative, because I'm reading f prime, so my zeros are my flattenings of the previous one, I can see my derivative is positive here, meaning I'm increasing. I'm positive here, so I'm increasing all the way to this flat. Then I'm negative to that flat. So I'm increasing to flat, decreasing to flat. All right? Well, what does that look like? Well, just like it is. It's a general sketch. It doesn't have to be perfect. So what am I doing? Well, I'm starting at a point, and I'm going to increase to a flat. I'm going to increase to a flat, and I'm going to decrease to a flat. Well, there's all my points right here. And as I look through here, here's my flat, here's my flat. Well, I can kind of look at this real easy and say, well, here's my beginning point, x equals -4, and that should not look as flat as it does because it's not flat, it's just increasing. So let me get my red, and I'll come down here and say, I increase to flat, and then I decrease. So all my flattenings, here's my x equals -2, here's my x equals 1, and here's my x equals 4. And didn't we have points of inflection in there? Where were all my points of inflection? Well, I had a point of inflection at -2. I have a point of inflection here at 0. There's my x equals 0, less than 1, and I also had a point of inflection. Where was my other guy? At 3, so somewhere right in here, there's my x equals 3. Okay, so that's generally or roughly what that graph would look like. I increased the flat, and I made this whole graph based off of checking out my number line on here, because this derivative is 0, meaning f prime is 0, so f is flat. Okay, and that's how I got that. So what we're going to do next is we're going to do a full analysis on this particular function, a complete analysis. And these are types of problems that are going to be on the AP test. They're not going to ask you everything about it. They're just going to ask you a couple things. So what we're going to do is we're going to use f prime to find this information, because the first derivative tells me increasing, decreasing, local max, local min. So in order to get that, I need to know what f prime is. Well, that's pretty tough. It's 4x to the third minus 12x squared, right? And that's my first derivative. So from here, to find out, I need my critical values. So I want to find out where the heck is f prime of x equal to 0, and when is f prime of x, when does it not exist? Okay, well, as I'm looking at this is a polynomial. I know this is not applicable to me. And that's why they like to do these with rational functions and piecewise functions. But then I'm just going to look here, and I'm going to take my 4x to the third minus 12x squared. When do you equal 0? Well, I see I have a GCF of 4x squared. That's going to leave me with what? An x minus, is that going to give me a minus 3 equals 0? So I can see I have flattenings at x equals 0 and x equals 3. Okay? So what I'm going to do to check, these are potential maxes and mins. Potential maxes and mins. I need to check these on my f prime line. And I'm going to put my 0 here. I'm going to put my 3 here because I know those are 0. All right? So then what I'm going to do is I'm going to check, when is this thing increasing and decreasing? Well, here is the function I'm going to look at to find out my signs. And I know this first one is always going to be a positive times. This factor is the one that's going to control whether it's positive or negative. So if I put a negative 1 in there, okay, my first 4x squared, well, you square negatives, it'll be positive. That's why that first one's always positive. This is going to be negative, meaning I'm decreasing there, isn't it? And then if I take a positive 1 and I put it in there, I'm going to have a positive. Well, 1 minus 3, that's still negative. So I'm still decreasing. We'll check it out here. Ooh, that's not a max or a min. I went from decreasing to flat to decreasing. Hey, that was a double root. Okay, and then I'm going to grab something on the outer end of that 3, and I'm going to put it in there. Well, it's still a positive, but now 4 minus 3, now that's a positive. So now I'm increasing. And I can read this super duper easy. F is increasing from where? Well, it's going to be increasing from 3 to infinity. That is the interval in which I'm increasing. When am I decreasing? Well, I like to see it as I'm decreasing from negative infinity all the way up to 0, union with 0 to 3. And yes, they'll let you say negative infinity to 3. I don't like that because then I don't see that flattening in the middle. Okay? Local maximum. Did this derivative have a change? So this is showing kind of, if I picture the graph, I'm going to make it out of orange. This is decreasing to flat to decreasing. No max or min in there. And over here, I'm decreasing to flat to increasing. Okay, so when I read my number line test here, I can see I have a local maximum where? I don't. There are none. Okay, where do I have a local minimum? Well, I do have a local minimum. I have a local minimum at x equals 3. Well, let's find out what that minimum is. So let's call it f of 3. What does f of 3 equal? Well, you can do the old synthetic thing, or you can just plug it in there. Either way, I got to plug 3 into the function to find what my minimum value is. And when I do plug that in, I believe I get negative 26. So there's my minimum value, and it occurs at x equals 3. Okay, so that's my analysis for increasing and decreasing. How about my analysis or concavity. Well, in order to find my analysis of concavity, I do need my second derivative. Well, here's my first derivative. So the second derivative is going to be 12x squared minus 24x, right? And my second derivative test, it's basically a ditto of the first derivative test, meaning I need to know when the heck is f double prime of x, when do u equal 0, and when does f double prime of x not exist, does not exist. Well, here again, this does not apply because it was a polynomial. Okay, my original function up there, polynomial, they're smooth and cruised everywhere. When does it not exist? Well, I'm going to take my 12x squared minus 24x, I'm going to set u equal to 0. And when I factor it, 12x is going to multiply by x minus 2 equals 0. So I know I have potential points of inflection at x equals 0 and at x equals 2. And they're not potential points of inflection because this is a polynomial. These will be, anytime my second derivative equals 0, they're going to be points of inflection. But what I'm going to do is I'm going to take my f double prime line and I'm going to place here at 0, I get a 0, and up here at 2, I get 0 for my double prime. And then what I'm going to do is I'm going to pick my points and carry the sign. First one I'm going to do is I'm going to plug in -1. Well, that's going to make this factor negative and this factor negative, meaning the second derivative is positive there. I'm going to take the number 1. That's going to make that first term positive, and the next one's still going to be negative, meaning concave down. Then I'm going to pick any number greater than 2, and I'm going to plug that in there. Well, that's going to make that first one still positive. Now 3 minus 2, that's a positive, times a positive is a positive. So I can see my concavity here. So I'm concave up from negative infinity all the way up to 0, union with 2 out to infinity. Okay, concave down where? I'm going to be concave down from 0 to 2. And I have a point of inflection. Well, I have two of them. I have a point of inflection at x equals 0 and at x equals 2. Notice, point of inflection. So I need the ordered pair for a point of inflection. Well, that's going to be 0, comma. Well, if I plug 0 into that function up there, automatically it's going to give me a 1, right? 1. And then I'm going to have one at 2, comma. What? Well, let's just synthetically divide just to remind people of their synthetic division if you're on a non-calculator. So I got a 1. I need a -4 for my cube. I don't have a squared. I don't have a linear term, but I do have a constant. And I'm going to hammer 2 through there. So I'll drop my 1. I get 2 is -2 is -4 is -4 is -8 is -8 is -16 is -15. So that means at 2 comma -15 is my point of inflection, and at 0 comma 1 is a point of inflection. Notice, I didn't skimp anywhere on work. Everything you see on this problem, I should see in your work somewhere, right? You should be able to analyze in this way. So the next thing I'm going to do here is I'm going to let you just do this one by yourself. I'm just going to write the answers in here. I'm not going to do it just for the purpose of keeping this video shorter, because there is one more big problem at the end that we're going to do, and that's going to take a skosh of time, hopefully not a lot. So I'm going to write the answers in so you got them. Hopefully you actually take the time to try this. So here are the answers to this problem. This one's the same as the other one. This one's, I don't know, it's just as easy as the other one. The numbers are just a little icky, all right? But notice when I'm listing my local maximum, okay, I'm listing f of -2, so I'm telling where it occurs and what it is at the same time rather than just an ordered pair. That's what I was taught to do all the time, because if you just list an ordered pair, it tells me where it occurs, not what it is. So I like to write it in function form a lot of times. So, and this is a -175 over 27. You know, if this were on the AP test calculator active, these are probably going to be rounded to the nearest 3 decimal places. Don't be calculator active all the time. Make sure you know how to do them. All right, last problem we're going to do here, and I'm going to have to pause because I have a different class coming in. I'm going to finish up in a bit. But is we're going to do a full analysis of a particle, a horizontal moving particle. The AP test, I guarantee you're going to have a particle moving along the x-axis with position function, x of t equaling something, and you're going to have to tell me, they're going to ask you when does the particle stop, when's it moving right, when's it moving left, when's it speeding up, when's it slowing down, and that's all through the analysis. So we're going to do a full analysis of velocity and acceleration on this devil when I come back here. So I will be back in a bit. All right, back for the attack here. Our particle problem. Forgot to put on there, we're going to look at, this is my position function right here, and we're going to look at that for t greater than 0, and time is going to be in seconds, which you would have to know in there. And when they say describe the motion, okay, what they're really asking is, when did it change direction? Okay. When did it change direction? When does it, changing direction, when does it move left as opposed to move right? We did all this earlier this year. When does it speed up and slow down? Okay, and it's a horizontal motion. They really love the horizontal motion problem. And we're going to do a full analysis on this dirty dog, okay? So V of t is actually going to be x prime of t, right? The first derivative, which is going to be 6t squared minus 28t plus 22, okay? And our a of t, okay, well, that's actually v prime of t, which could be x double prime of t, just see the connections of everything down the line, okay? That's actually 12t minus 28, okay? And I know my v of t is going to be in something per second, and my a of t is going to be something per second squared. Well, it's not defined in feet or anything here, so we're just going to move along. So what we're going to do is we are going to explain, or we're going to examine v of t. Now, when v of t, come on, trying to get this done in a short time so your video is not crazy, but when v of t actually equals 0, we know we are stopped. Okay? And we should know or remember when v of t is greater than 0, that really means it's positive. It moves towards the positive x values or right. And when v of t is less than 0, it moves left or towards the negative. That's how I always remember that anyway, okay? So what we need to do is we need to take our v of t, which is going to be 6t squared minus 28t plus 22. What we're going to do is we're going to factor this. Well, hopefully, we're going to look at this guy. Hopefully we see that there is a GCF of 2. We want to know when it's 0. So we're going to pull that 2 out, 3t squared minus 14t plus 11. And yes, that does help our factoring abilities here, because now I have 3t times t, and it really wouldn't make sense to put an 11 over here because that's going to give me 33. So I'm going to put 11 here and 1 here, and I know I need negatives, so they're both signs are the same, so I'm going to put 2 minuses there. So I know, I found out when t equals 11/3 and when t equals 1, this little bugger is stopped. Okay, so I'm stopped at t equals 1 and negative 11. It stops here. And did it change direction there? I don't know. Just because it stopped didn't mean it changed direction, just like on your way to school. When you stop at the stop sign, you go through the stop sign, you did not change direction. So I'm going to call this my x prime of t line. I'm going to put my 1 on here. I got a 0. I'm going to put my 11 thirds on here for a 0. And for you decimal freaks, 11 thirds, well, that's what? 3 2/3, just a hint less than 4. And then what I'm going to do is I'm actually going to take my v of t at 2 times 3t minus 11 and t minus 1. And I'm going to test this. Now my interval is not going to go forever over here. It's actually stopping. And where is it stopping? Okay. It's actually technically stopping at 0. Why? Because this problem is going to be good for t greater than 0. Well, the nice thing about that is that endpoint is not a critical value, so I can use that to check for up and down, or I can use that in my derivative. So I'm going to use that 0 to find out what is my particle doing between 0 and 1. And if I put a 0 in there, I'm going to have what? A negative times a negative, meaning it's a positive, okay? Which means it's moving right here because velocity is positive, so I'm going to be moving right. And then between here, I'm just going to pick the number 2. And if I put a 2 in here, this one's still negative because it's 6 minus 11, but this one's positive. Negative times a positive is a negative, so now I'm moving left. And then I'm going to pick anything outside here, anything bigger than 3 2/3, maybe 5. Okay, if I put a 5 in there, that's 15 minus 11. That's now a positive number. And this is a positive number, meaning, hey, now it's positive again. I'm moving right. Okay? So when I'm describing this motion, I'm stopped. I'm going to kind of come back here, and I'm just going to cheat up a little bit. And I'm going to say stopped at these values. And then I'm going to give my intervals for right and left. Okay? So I'm moving right, and it's moving right from where? From 0 to 1, and then it's moving right again, union with 11 thirds to infinity. Okay? A lot of times they're going to have an end interval on here, but they're going to say justify your reasoning. Well, how do I know that? I know that because x prime of t is greater than 0, therefore it's moving right. That's my justification. Okay? When am I moving left? Well, I'm moving left from 1 to 11 thirds. They're going to say justify your reasoning. Well, my justify is because x prime of t is less than 0. Okay? So that's how I know I'm there. And I'm changing my direction. And I don't even have to say x. I can call this, rather than call it x prime, I can say v of t because it's my velocity. As long as you're identifying it as the derivative, you're fine. So now the next thing we're going to do is we're going to examine the acceleration function. Doesn't that sound like fun? What is my acceleration function? Well, I got to look up. My acceleration is, ooh, that's a hard one. A of t is 12t minus 28. A of t equals 12t minus 28. Well, I'm kind of a factor freak. We do want to know when a of t is 0 or undefined. I guess I should have talked about that back here, but I'm only worried about my critical values of increasing and decreasing because this is following, okay, a polynomial function. I'm not worried about the undefined when critical values, only the zeros. And ditto down here for my acceleration. But I'm a factoring freak, and I can see there's a 4 anyway that come out of these two. So that's really 3t minus 7. So I know when t equals 7 thirds, okay, that's when my acceleration is 0. And when I'm thinking about acceleration, okay, I should be thinking about what I should have talked about. Whoa, move that there. What the? that over here. Okay, well, that's going to work. Come on, baby. Oh, boy. Okay. What I should have talked about over here really quick, like I did with velocity, is I should have said, well, if acceleration is greater than 0, what that's actually doing is that's making me be kind of pulled right. Okay? And when A of t is less than 0, think of it as being pulled to the left. Okay? And we know, why did I just do that again? And we know that when acceleration and velocity are the same sign, okay, when they're the same sign, they're working together. Therefore, if they're both negative, I'm being pulled left and moving left. When they're both positive, I'm being pulled right and moving right. That is why it is speeding up in those cases, all right? So I found my second derivative zeros, and we want to know, when is this thing going to be pulled to the right and pulled to the left? Well, we're going to look at that right here, because we're going to take our, I'm going to call it my x double prime of t line, or, which is a of t, all right, either way. And I'm going to put my 7 thirds on there. What is that for the decimal freaks? That's what, 2 2/3-ish? And here I'm 0. So what I need to do is I need to identify right in here for my concavity test, and I'm going to say, hey, I'm going to put a 0 in there because I know it's going to be negative then, isn't it? Meaning being pulled left. Okay? And then I'm going to put something on the other side, like maybe 4. And when I put my 4 in there, you get 12 minus 7, which is a positive number. So I'm going to be pulled to the right on the other side of 7 thirds. So if I had to examine this a little bit, I'm really kind of thinking that I'm being pulled to the left on the interval from 0, and that's my endpoint, I should have said. Okay, they go all the way from 0 to 7 thirds. And when they say, how do you know you're being pulled left? Because, and it doesn't matter, I'm just being consistent. Intervals, I'm going all in on parentheses unless it's domain and range, then they want to know. But A of t is being pulled left because A of t is less than 0. That's my justification. And I'm technically being pulled to the right from 7 thirds to infinity, because I don't have an endpoint here listed out. And my justification is because acceleration, or A of t, is greater than 0, therefore it's being pulled to the right. Okay? So that's just modeling what I have coming on here. And what I want to do here for the final thing, okay? Final thing, this is pulled left, pulled right, and that's, you know, that's Kruger shorthand. Moving right, moving left, moving right, okay? But that's really not there because I'm just doing it over here. I'm just doing some stupid shorthand there. And the last one, I guess, I want to examine them all together at the same time. I want to examine V of t and A of t all together. So in order to, oh, son of a biscuit, in order to do that, I'm going to come down here, and I want all my number lines together, okay? And I want to go there. So what I want to do is I want to put my V of t line, and here I went from 0 all the way over. This is going to be my V of t line. And as I'm looking at my V of t line, okay, at 0 was my endpoint. At, I believe it was 1, I had a critical value of 0. And at 11 thirds, I had a critical value of 0. And then it kept going on. And what I did notice is I was moving to the right I was moving to the left, and I was moving to the right. That's all on my previous analysis, okay? And then I also have my acceleration function here, which I want to parallel kind of underneath this guy. And if I think about this, 7/3, well, 7/3 is somewhere in here, okay? And I was 0 there, and on my acceleration, I was being pulled to the left right away, and I was being pulled to the right. Now, when I do my analysis of acceleration and velocity together, what I really need to do, this is where my speeding up, slowing down stuff happens. Okay, I want to split this, and I need to get an analysis everywhere that my derivative, that on either critical value, meaning I want to split it here, I want to split it here, and I want to split it here, okay? And I want to see my analysis of what's going on both of these. So when I'm looking at that, I can kind of think about this underneath here. And on the interval from 0 to 1, what is happening there? I am interval from 0 to 1, I'm moving right. And I'm moving right, yep, need an H there, because v of t is greater than 0, and I'm slowing down, so I'm moving right but slowing down, and I'm slowing down because, and over here I can justify this all, v of t is greater than 0, which means I'm moving right, and I'm slowing down because a of t is less than 0, meaning they're working against each other. I got a positive here and I got a negative here. Okay, so I'm moving right and slowing down. So as I look at my next interval, which I'm talking about from 1 to 7/3, what am I doing? Well, now I'm moving left, right, because it's negative, and my acceleration is negative, but I'm moving left and speeding up. Speed up because my signs are the same. This is negative on this interval. So moving left, left, and speeding up. And my justification is, well, I'm moving left because v of t is less than 0, and speeding up because a of t is the same sign. Therefore, I'm moving left and speeding up. Okay? What's happening from my 7/3 to my 11/3? Well, what I can see is I can see I'm going left because velocity is negative, and I'm positive here, so I'm slowing down. And I'm only slowing down because positive and negative signs, so moving, what did we say? We said left and slowing down. Justify your answer? Well, I'm moving left because v of t is less than 0, and I'm slowing down because a of t is now positive. They're not working together anymore, okay? They're working against each other. Now, last one. I got to move these up. This always impresses me. I'm just going to juke and drive them all up so I can fit that last one on there. And now I can see from my interval from 11/3 to infinity, right? What's happening? Well, I'm moving right, moving to the right because velocity is positive, and this is positive, so I'm speeding up because these two are the same. That's what's making me do this. That is making me go right, and the combination of acceleration and velocity together makes me move right, makes me speed up. So I'm moving right and speeding up. Okay, and they ask you these questions on the AP test, and if you don't justify it, they consider it a bold answer. And A of T has to be the same sign, and those are my justifies. These are justify here, and these are describe the motion here. So describe the motion and tell me how you know that's your justify, all right? So, and we know it changes direction. Well, I could take a quick gander at the graph, and if you, wrong one. If you read the graph, this is the graph of it. I can see, because I'm negative, I'm speeding up, or excuse me, I'm moving left, moving right, moving left, moving right, and you can just read that on your position graph once you're there. But I'm not going to explain that anymore because we're already deep into our day. Have a good rest of your day.